Hello friends, I welcome you in lecture number 16 on convergence of series. In this session we are going to discuss this question which was asked in GTU Summer 2019 exam. Here we have to check the convergence of the series sigma n equal to 1 to infinity minus 1 raised to n times square root of n plus square root of n minus square root of n. So at the first moment we can see that because we have minus 1 raised to n in the multiplication, we can say that this is an alternating series because terms are alternately positive and negative. Now if we have alternating series, then we have Leibniz rule for testing its convergence. And what is Leibniz rule? That suppose we have this type of alternating series sigma minus 1 raised to n times say un, n equal to 1 to infinity, then this alternating series is convergent if three conditions are satisfied. First condition is all these terms un are positive for all values of n, and this sequence un is decreasing, that is un is greater than un plus 1 for all n, and third condition is limit of un as n tending to infinity is 0. If these three conditions are satisfied, then we can say that given alternating series is convergent. Now if any of these three conditions is not satisfied, then we cannot apply Leibniz rule or alternating series test. So in that case we have to think for another test. This alternating series test or Leibniz rule gives us the conditions for convergence of alternating series. If these three conditions are satisfied, then series is convergent, but if at least one of these three conditions is not satisfied, then this test fails. We cannot say that if limit of un is different from 0, then series is divergent. This test is applicable and for checking the convergence in this way, that if these three conditions are satisfied, series is convergent, but if any of these three conditions is not satisfied, then the Leibniz test fails to check the convergence of the series. So in that case we have to think for another convergence test. Now you can see this is an alternating series. So at the very first moment you may have the idea about this alternating series test or Leibniz rule or Leibniz test. So for example, suppose we apply Leibniz test, then we can see that this quantity is un. If we compare with sigma minus 1 raised to n times un, then we have un equal to this quantity square root of n plus square root of n minus square root of n. So we should check all these three conditions for that quantity un. Suppose we start with first condition, then it is obvious that this is always going to be positive. We can check randomly by taking different values of n, and this quantity is always going to be positive, or we can say that n plus square root of n is always greater than n, and therefore if we take square root on both sides, then this is always true, therefore this difference is always positive. So this remains greater than 0 for all values of n. Now second condition, for second condition we have to do some exercise, or we have to check whether that series is sequence is decreasing or not. So for the time being we check third condition. Suppose we try to find out limit of this limit n tending to infinity square root of n plus square root of n minus square root of n. Suppose we are interested in the limit of this quantity. Then if I want to find out this limit, if I take n tending to infinity, then I will get infinity minus infinity form. So I cannot apply L'Hospital rule to decide this limit. So instead of that, what I can do is I can consider multiplication by this quantity n plus square root of n plus square root of n. I multiply and divide by this quantity. Square root of n plus square root of n minus square root of n is multiplied with square root of n plus square root of n plus square root of n, and because we are multiplying with this quantity, we have to divide with this quantity. So we are rewriting this in this way. We are considering positive sign here and we multiply and divide by that quantity. Now we simplify this. This is limit n tending to infinity, and here we have this quantity as it is, n plus square root of n plus square root of n, and here if you notice we have something minus something and something plus something. That is, we can apply this formula: a minus b into a plus b is equal to a square minus b square, with a equal to square root of n plus square root of n and b equal to square root of n. So I have to square this quantity and it is in square root. So if I take square of this quantity, I will obtain n plus square root of n, and minus square of this quantity, that is square root of n, that is n. And let me rewrite again. We can cancel out n in the numerator. This n will get cancelled here and we are left with square root of n here, and here we have square root of n plus square root of n plus square root of n. So here we have infinity by infinity form. So if we wish, we can apply L'Hospital rule, or we can find out the limit without applying L'Hospital rule also. So to find out limit, I am dividing numerator and denominator by square root of n. Okay, I am multiplying by 1 over square root of n and 1 over square root of n, numerator and denominator. So this into 1 over square root of n, that is 1, and here this quantity divided by square root of n. Therefore we have this type of quantity here, n plus square root of n divided by square root of n plus square root of n divided by square root of n, that is 1. Now we again simplify here. This is limit n tending to infinity, and because I have two quantities in the square root, I have this type of situation here: square root of a divided by square root of b, so that I can write as square root of a divided by b, that is square root of n plus square root of n divided by n and plus 1. Now we again simplify this denominator, limit n tending to infinity. Here I have 1 and here I have 1 plus, we write one more term, square root of n divided by n. N divided by n is 1, square root of n divided by n, and plus 1. And this again we can write as limit n tending to infinity, 1 divided by square root of 1 plus 1 over square root of n. This n can be written as square root of n. So 1 square root of n will get cancelled, and plus 1. And now if I take n tending to infinity, I have limit of 1 as 1, square root of limit of 1 is 1, plus limit of 1 over under root n as n tending to infinity, that is 1 over infinity is 0, and plus 1. So finally we obtain 1. That means limit of this quantity is 1, that is it is different from 0. So this third condition is not satisfied. If we have alternating series sigma minus 1 raised to n times un, then we must have limit of this un equal to 0. But here limit of un is non-zero, and therefore we cannot apply that alternating series test or Leibniz test. So we have to think for another test. So you can think that the first test which comes in our mind is nth term test for divergence. If you remember the nth term test for divergence, suppose I have some series sigma an, and if I find out the limit of nth term of the series, and if that limit does not exist or limit is non-zero, different from 0, then we can say that given series is divergent. So here we can apply that nth term test for divergence, and for that I have to find out the limit of nth term of given series. Nth term of given series is minus 1 raised to n times square root of n plus square root of n minus square root of n, and this we can write as limit n tending to infinity minus 1 raised to n times limit n tending to infinity square root of n plus square root of n minus square root of n, and we have just obtained limit of this quantity, and that is equal to 1. We have obtained limit of square root of n plus square root of n minus square root of n, that is limit of this quantity is 1. So that we substitute here, this limit is 1, so we have limit of minus 1 raised to n tending to infinity, and we know that this limit does not exist, because if n is even, this quantity is converging to 1, and if n is odd, this is going to near to minus 1. Therefore this limit does not exist, which does not exist. That means limit of nth term of given series does not exist, and therefore by nth term test for divergence, given series is divergent. Therefore by the nth term test we can say that given series is divergent. So here it is an alternating series, but alternating series test is not applicable because limit of this quantity is different from 0. Therefore this condition is not satisfied. But if we find out limit of nth term of given series, then we find that that limit does not exist, and we can easily conclude from the nth term test or divergence test that given series is divergent. So be careful. It is not necessary that whenever you have alternating series, then it is always convergent by Leibniz rule or alternating series test. This is an example of alternating series whose convergence is decided using nth term test for divergence, and we know that if limit of nth term of given series does not exist or non-zero, then given series is divergent, and here we find that limit of this nth term of given series does not exist. Therefore by nth term test for divergence, given series is divergent. So all you have to show in this to write down the answer, you have to first find out limit of this quantity as I have explained here. So first I obtain the limit of this quantity which is multiplied with minus 1 raised to n. Okay, we are considering this standard form for alternating series. If alternating series test fails, then First we can decide the limit of this quantity, which is multiplied with minus 1 raised to n, and after obtaining limit of that quantity, we can find out the limit of minus 1 raised to n times this quantity. And here we are applying the limit rule for two sequences. We know that limit of an into bn as n tending to infinity is equal to limit of an times limit of bn, and we have already obtained limit of this sequence, that is 1, and we know that this sequence is divergent. Therefore given series is also divergent because limit of nth term does not exist. So this is very nice question. It was asked in GTU Summer 2019 exam, and we are able to decide its convergence using nth term test for divergence. And here we find that because limit of nth term is does not exist, this series is divergent. So this is all about this session. I hope you like it. Thanks for watching.